Hello everyone. In the last class, we started seeing how practical 2D and 1D channels look like. How do we sort of need to analyze those things in those channels in more with more nuances. And so today we will complete this part and we will begin with the introduction of MOSFETs. Okay, so let me quickly review what we have been doing in this. In last few classes, we have been discussing how the notion of resistance and conductance is different in classical understanding, in the conventional understanding, and how it is different in the general model of transport, both for 1D, 2D and for all 1D, 2D and 3D conductors. Apart from this, we saw that in a ballistic conductor, the power dissipation takes place at the contacts. Half of the power is dissipated at the left contact and half is dissipated on the right contact. Similarly, the voltage drop also takes place on the contacts. And this is actually quite opposite to what happens in the conventional macroscopic devices. Okay. So these are some new things. So ultimately, the equation to begin with, or the central equation to calculate the conductance is this. And please keep in mind that this is true for near equilibrium transport. Near equilibrium means that we are not applying high voltages, because in that case F1 minus F2 cannot be approximated by the just by the first order of the Taylor series. Okay. So with this background, we started discussing how 1D and 2D resistors, practical 1D and 2D resistors are different from the ideal cases. In a realistic 2D conductor, apart from its length and width, we also have a finite thickness. And that we need to actually take into account while doing the calculation, doing the calculations for the current in a channel that is 2D channel. Okay, so there is a finite thickness, so the electrons will be confined in this direction because this is of the atomic scale, and because of the quantum mechanical confinement, electrons' energy will be discrete. So in the confined direction, generally the energy of the electrons is given by this number. So the epsilon n energy is n square pi square h bar square divided by 2 m star a square, where a is the extent to which electrons are confined, the carriers are confined. So in this case, instead of a, we might have t, because t is the thickness in which electrons are confined. So and in two directions, if we just consider two directions, if we consider an ideal 2D conductor, the energy of the electrons can be, in two dimension, the energy can be h bar square k square divided by 2 m star. Okay. So let us consider the case of a practical or a realistic 2D channel. In a realistic 2D channel, the electrons are confined, again the electrons are confined in z direction. If this is the z direction, electrons are confined in this direction, and electrons are free to move in x and y direction. Now if we just see the confinement in the z direction, this is the thickness t, and because of this confinement in this dimension t, the energies will be discrete. The energy of the electrons will be discrete, and this energy will be given by these numbers. And if we start this calculation, the energy of the first level, let us say epsilon 1, of the second level call it epsilon 2, for third level let us call it epsilon 3. So epsilon 1 is essentially pi square h bar square divided by 2 m star t square. Similarly, epsilon 2 is 4 times epsilon 1 and epsilon 3 is 9 times epsilon 1. Okay. And please keep in mind that these are the energies because of the confinement in z direction. Z direction. Okay. In xy direction there is no confinement, electrons are free to move, or we can say that relatively the length and width of the semiconductor are large, so electrons energy is not properly discrete. It may have bands and band gaps because of xy direction, and there will be from the EK diagram we or from the EK relationship we might have this parabolic relationship, especially near the band edges. So now any electron that exists inside this device, any electron, this energy of this electron will be the summation of the two components, the energy because of the motion in xy direction and energy because of the motion in z direction where the motion is confined. Okay. So now there is an interesting fact here. In xy direction the energy can be as low as 0 actually. So energy can go to very low levels. Okay, so this EXY typically it can be from 0 to any high values. But EZ, the energy in the confined direction, this is the discrete values and this is always greater than 0. So it is never 0. Even the lowest possible state has a non-zero energy which is given by this value. Okay. So if let us say if the electron has energy epsilon 1 in z direction, or electron is in the lowest possible state in the z direction, then because of the energy in xy direction, electrons energy, the total energy of the electrons, which is essentially the sum of EXY plus EZ, and here if we put EZ to be epsilon 1, so it would be EXY plus epsilon 1. So those for these electrons the energy can be anywhere from epsilon, because this EXY can go from 0 to high values, very high values as well, or a certain value let us say. So the electrons may have energies from, so the electrons that have energy epsilon 1 in z direction may have total energy anywhere from epsilon 1 to a high value. All right. So this is the these lines essentially show that the electrons can have any energy from epsilon 1 to high values. And but the electrons, let us say the electron, if the electron is sitting in epsilon 2 state or in z direction, the electronic energy is epsilon 2. In that case the total energy of the electron will be EXY plus epsilon 2, and this value can go from epsilon 2 to a very high value. So the electrons sitting in this state in z direction may have any energy starting from epsilon 2 to a very high value. So this may be the energy of electrons in the total energy of the electrons, those electrons who are sitting in the epsilon 2 state. So now an interesting situation arises. The electrons that are in epsilon 1 state may have energies here in this regime. So, in this regime also the electrons with energy or electrons sitting in state epsilon 1 can have energies in this regime. Similarly, the electrons sitting in state epsilon 2 can also have energies in this regime. Electrons sitting in state epsilon 3 can have any energy above epsilon 3. So, they can have any energy here, or electrons sitting in epsilon 1 can have any energy, total energy to be this. Okay. So, now this overlap here in this range, electrons can exist in two configurations in this range. They can be sitting in epsilon 1 state and have energy sufficient so that their total energy is in this range, or they can be sitting in epsilon 2 state and have the energy equal to the difference between epsilon 2 and energy in this range. So, these two are different configurations and these two are allowed configurations for electrons, and this leads to a sort of degeneracy in the systems. Okay. Because now there are two type of electrons that can take this energy in this range, and these are known as the subbands, overlapping subbands. Similarly, in this range, electrons sitting in epsilon 1 can also have energy, electrons sitting in epsilon 2 can also have energy, and electrons sitting in epsilon 3 can also have energy in this range. And here the degeneracy, or there might be three configurations of electrons in above epsilon 3. So, in other words, what we can say is that these kind of solids have subbands starting from the discrete energy levels because of the confinement. So, the discrete energy levels are because of the confinement in one direction, that gives epsilon 1, epsilon 2, epsilon 3 in the direction of confinement. Now, because of the free motion in other two directions, electrons energy can be from 0 to any value, and in that case the electrons might have an energy configuration in which their energy can be epsilon 1 in z direction and exy in, or any arbitrary energy in xy direction. So, electrons might have a subband at epsilon 1, another subband at epsilon 2, another subband at epsilon 3, and some of these subbands may be overlapping with each other if these energies are not sort of far apart from each other. Now, something interesting happens in this case. Let us say we have, this is the channel, this is a real 2D device as has been shown here. This, we are making a two terminal device with this 2D conductor, this realistic 2D conductor. So, what it means is that we are putting contacts on two sides of it, and please always keep in mind that these are bulk contacts. So, so we are putting contacts on this device. This is the source contact, this is the drain contact. Now, the Fermi level of the system is, let us say, here, somewhere here. EF is this point. Okay. Now, if we need to calculate the total number of electrons in this system, in this channel, at T equal to 0 Kelvin, let us say, which means that all states up to the Fermi level are filled. Okay. So, all the states up to this Fermi level are filled, which means that, and how many states can be there up to the Fermi level? So, let us say this was our original potential box, this is epsilon 3, this is epsilon 2, and all the states below the Fermi level are now filled. There cannot be any allowed electronic state below epsilon 1, that is disallowed by the quantum mechanical nature of the electrons. So, it means that in this particular case there are two discrete states below EF. So, there can be two subbands in the system, and the number of electrons in the system will be because of this subband and because of this subband, which means that there are two configurations of electrons possible in this system. One is those electrons that have energy epsilon 1 in z direction and any energy from 0 to EF minus epsilon 1 in xy direction. Similarly, the second configuration can be that the electrons might have energy epsilon 2 in z direction and any energy from 0 to EF minus epsilon 2 in xy direction. So, that is why we need to calculate, generally the formula to calculate the number of electrons is the density of states times the Fermi function dE. Now, in order to account for both the subbands, and this is from 0 to infinity for all possible energy states. Now, we need to do this from 0 to or epsilon 1 to EF because of the first subband, or let me write it in a more cleaner way. The number of electrons in the system will be epsilon 1 to EF because of the first subband, and GE is the density of states. So, GE is the density of states. FE, the Fermi function below Fermi level, will be 1 at T equal to 0 Kelvin. We are assuming the case to be T equal to 0 Kelvin. So, it will be 1 times dE plus, because of the second subband from epsilon 2 to EF, GE times 1 times dE. Okay. So, in a way this will be N is equal to epsilon 1 to epsilon 2 GE plus GE dE plus twice epsilon 2 to EF GE dE. So, this could be the total number of electrons in the system. So, this we need to keep in mind actually while doing calculations for the realistic 1D and 2D conductors, that now the subbands are formed because of the confinement in the smaller atomic dimension, and those subbands may result in degeneracy in the system, and that we need to keep in mind and that we need to take in account in all our calculations. Okay. So, similarly, this was the case of a practical 2D conductor, a real 2D conductor. Similar analysis will hold for a 1D conductor as well. In 1D conductor, we will have confinement in two directions. So, the potential well will be in two directions and electrons are free to move in one direction, so that the total energy, so in a real 1D conductor, let us say this is x direction, this is y direction, this is z direction. So, the electrons are confined in y and z direction, and the total energy is Ex plus Eyz. And now this Eyz is now a discrete value, will be a discrete value, and that is what essentially we need to take into account now. Okay. Like we did for, so there will be subbands, and now the subbands will be even more, because this potential will now be in two directions, and we need to solve for the potential for electron confined in two directions. So, accordingly we will obtain the discrete energy states, and based on those discrete energy states the subbands will be there, and all those subbands need to be taken into account while doing calculations. Okay. This analysis is pretty much similar to the analysis of the 2D channel. Okay, so so just to sum it up, the confinement results in the formation of subbands, and these subbands are based on the discrete energy levels that arises because of the confinement. If the confinement in 1 and 2D resistors or if the confinement direction is extremely thin, subbands are far apart from each other, and if not, subbands are very closely spaced. So, if a 2D conductor is extremely thin, it might happen that the subbands are very far apart from each other, and it does not make any difference in that case. So, for example, if epsilon 1 is here, epsilon 2 is here, or maybe the higher energies are even higher, and if the Fermi level of the system is here, in that case there will be just this subbands will not come into picture, because yes, there will be only one subband that will affect the system, and that will be this one. By taking subbands into account, the expressions that we derived previously will modify like this. So, the expression for the modes will modify in this way. We need to take into account all the subbands, and even in the expression of even with energy corresponding to a subband, we need to take into account this epsilon n number here. There is this another number that is written as GV. This is known as the valley degeneracy. So, typically what happens is that sometimes in the EK diagram of the semiconductor, we might have a situation like this. This is the EK diagram, or energy axis can be here as well. So, in this case what happens is that at the bottom of the conduction band or top of the valence band, there are multiple solutions, or multiple EK plots overlap with each other generally at the band edges. So, in this case what happens is that we need to, so the electron can either follow this curve, or it may sit in this band, or it can also follow this curve. So, at this energy electron has two choices to take for the EK relationship for the wave function, and this introduces another kind of degeneracy, that is known as the valley degeneracy, and this is given by GV. Okay, so if there are two EK plots, two EK curves, or two bands that are overlapping with each other right at the bottom of the conduction band, then the valley degeneracy will be Gv. Okay. So, there are two kind of degeneracies that can come into picture. One is because of the overlapping bands, and second is because of the subbands, and both of them we need to account while doing calculations for the number of modes in our practical devices, in our realistic devices. So, this summation is over the subbands, and corresponding to a subband there is this epsilon n energy. So, finally, just to sum up everything, the number of subbands or the number of modes in a 1D conductor, this number of modes in a 1D conductor is actually 1 in 1D conductor, but because of the practical constraints, because of the confinement in two directions, the number of modes will be equal to the number of subbands. Okay. In ideal 1D conductor it is 1, but in a practical realistic 1D conductor it might be, it is equal to the number of subbands at energy E. In a 2D conductor, the number of the modes are given by this expression. Modes are Me is in a 2D conductor, Me is given as W times M2DE, or it is written as mGv if Gv is the valley degeneracy, square root of 2m star E, or generally like this. But now with subbands we need to modify this expression like this. We need to sum over all possible subbands, and in addition we need to introduce this energy term here in the square root as well. Okay. Similarly, in the 3D practical resistors, this is for the 2D case. In 3D case, the number of modes expression is actually given by the area of times M3DE, which is m star E minus EC divided by 2 pi h bar square. And if Gv is the valley degeneracy, this Gv will appear here, and this will not change actually, because the practical 3D conductor is actually the way an ideal 3D conductor will look like. So, with these modifications in number of modes, now we need to modify the expressions for the conductance, because here we need to take the average of modes in the Fermi window, and we need to take the average of the transmission coefficient or average of the scattering mean free path in each mode over the Fermi window. So, this will also get modified accordingly. This will be, all these things will be modified, and finally in a practical when we sort of have a new device, when we have a new material and we want to make a device out of it, we first need to calculate its density of states, then number of modes. From there we can calculate the, and in addition we also need to calculate its transmission coefficient if it is a bulk device, or if scattering is happening we need to calculate the mean free path or transmission coefficient. Then depending on the carrier confinement in other directions, we need to find out how many subbands arise in this system, and by taking all that into account we can finally calculate the device parameters, device IV characteristics and conductance or resistance of the device. So, this is how things actually work in real life. Okay. And okay, so this is the expression for the conductance in a more general case. So, all these things will be modified if we take the subbands into account. So, in summary, what we have is while we need to calculate the conductance of the system, we always start with this expression, okay, and this is true for the near equilibrium transport. If the transport is not near equilibrium, then we will start with the current equation. Okay. Then we have seen here that conductors have finite resistance even in the absence of scattering. So, even in the ballistic case, the conductors might have finite resistance, and that is because of the scattering in the contacts. Okay. We also saw how to use conductivity equation when temperature is uniform across the conductor. If the temperature is varying, that will result in variation in the Fermi functions, and that will also need to be taken into account. That we will see while discussing the thermoelectric systems. This ballistic resistance, that is the resistance in the absence of scattering in the channel, that sort of sets a lower limit to the resistance no matter how short the resistor is. Okay? And this is also known as the quantum of resistance, and this is given by this formula, or 1 by 12.9 kilo ohms. Transport from the ballistic to diffusive limit can be easily calculated if we know the scattering mechanisms. So, by knowing scattering mechanism, I mean we need to know the mean free path, and we need to know the transit time in the channel. So, if we finally, if we encounter a new material or a new nanostructure, and we need to know its resistance or its IV characteristics, we need to begin with these set of equations that we discussed in our general model of transport. And this slide essentially reviews all those equations that we discussed in detail. So, with this we will now see how a MOSFET actually works, and especially a nanoscale MOSFET. In this, there is one missing point that we have not discussed, and that is the derivation for this mean free path. Okay. So, if time permits, we will do that later, but that is not extremely essential in order to understand this entire dynamics. Okay. Okay. So, in the next class, we will begin with the discussion on the basics of MOSFETs, and then we will move to the nanoscale MOSFETs. Thank you for your attention. See you in the next class.